RF Man here. So this will be part 4 of Class E Amplifiers Explained. It will be the final part of the 4-part series. And as you might recall, we left off part 3 looking at this software tool that can be used to simulate a Class E circuit. These are based on Sokal's design equations. And just as a quick summary, we were going to design an amplifier running at 13.56 megahertz at 30 watts, 24 volts into a 50 ohm load. So we went through the calculations and determined the values for L and C. As you recall, this is the shunt capacitor, and then we have the resonator, and then we have our matching circuit. So this tool has the capability of exporting to LT Spice. So just click that. If you have LT Spice loaded, it will create the file for you, and then you can go ahead and simulate the waveforms. Now, what I'm looking at specifically here is the turn on and turn off point of the IRF510 transistor. So we're basically looking at the IDS current and IDS voltage. Now, this is an ideal switch that's available in the libraries for LT Spice, and you would expect that if you're using an ideal switch with no parasitics, that it would give you the ideal Class E waveforms. And that's basically what we've seen on some of the other slides, where we have 0 volt switching when the transistor turns on, and then we have 0 current switching when the transistor turns off. So that's what's illustrated there, and again, that's what you'd expect to see with an ideal perfect switch with no parasitics. So that's what it looks like. And if we go ahead and we substitute the perfect switch with the actual component using the SPICE model, here we see the IRF510 in the circuit with the same component values, and you see the waveform looks quite different. And again, that's because of the parasitic effects that are modeled in the LT SPICE model for this device. And you can see we do have a little bit of overlap during turn off in the simulated waveforms. The front end looks good. During turn on, voltage drops, current rises, as I said, and it's very close to 0 volt switching, so there's very little power being dissipated because the voltage is basically 0 before the current rises. But here on the other side, when it turns off, right, the current drops, the voltage rises, but you can see the voltage starts to rise before the current goes to 0. So we do have a little bit of power dissipation there in the model. So this is just a look at what happens if we take the load network and remove it from the circuit. You probably recognize this waveform as being very, very close to the Class B waveform, where we have the current and voltage overlapping during turn on and turn off, and therefore we have a lot of power being dissipated and a lot of power being wasted. So here's the waveform that I captured without the load network. Looks similar to the LT SPICE model, and you can see the overlap there. Again, it looks almost the same as a Class B. So I took the original calculated values from the software tool that we demonstrated, and in Nathan Sokal's paper titled Class E RF Amplifiers, he describes a procedure where you can optimize the circuit by varying the values of the load network, okay? Values of the inductors and capacitors. And he basically describes when to increase or decrease the capacitance and inductance based on the shape of the waveform. Remember that the resonator is reshaping the current waveform. So I went ahead and I attached this to my presentation, so we can go ahead and quickly open this. And here's his white paper. And if we go down to page 15, here we see that same drawing. Okay, and then there's a step-by-step procedure to follow to try to optimize the waveform, to reduce the crossover and achieve 0-volt switching. Now, will it be absolutely perfect? No, but you'll be able to minimize the amount of overlap between the voltage and current and dramatically reduce the operating temperature of the device, and at the same time, of course, increase the efficiency. So I'm not going to go through this. I will have this link in the video description, and there again is a step-by-step procedure, and it's pretty straightforward. I followed it, and I used basically LT Spice plus the actual circuit, and in some cases I put trimmer capacitors in and adjustable inductors, and I was able to optimize the circuit values. So this is what it looks like after optimization, and these are the component values. So I went ahead and combined all the inductors, so I came out with 51 picofarads for the shunt capacitor plus the 81 picofarads for the output capacitance of the transistor. So you have to add those together. That's 132. And then we've got 700 nanohenries. That's both inductors combined. And then the capacitor values you see there, 560 picofarads and 331. So I used LT Spice to aid me in doing this, following the methodology I just described. And then when I had the circuit on the bench, I had to change the values a little bit up and down as well, due to the parasitics of the PC board, the distance between traces, the length of the traces, etc. So that's what the final circuit looks like with the final values. And I went ahead and modeled that and then measured the overlap, and it looked very similar to the LT Spice model. So I'm going to go ahead and set this up on the bench, and we can look at the actual waveforms to see how they compare with the simulation. And then toward the end of the video, we're going to calculate the efficiency while monitoring the temperature, and then compare that with our original measurements for the Class B amplifier. All right, so here's my setup. Basically the same setup that we had for Class B. I'm using my current probe to look at the drain current and the scope probe to look at the drain voltage. And I've got basically a 50 ohm dummy load, and I'm running it at the same voltage, 24 volts. So you can see that on my power supply voltage and the current. And again, let me just describe, we've got for the Class C amplifier, the RF choke here, and we have a shunt capacitor. I put in a trimmer so I could optimize that value, and then we have basically the load network, which is LX, and the two capacitors that are used in the resonator circuit and also the matching circuit. So all I did here was combined the inductor values into a single inductor. And I mentioned in the other video that has to be a high Q inductor. So basically I was able to use a powdered iron core, and to reduce the resistance, the core allows me to use less windings to achieve the same value of inductance, and I used a heavier gauge wire. So remember, the Q is the ratio between the inductive reactance and the resistance, so you want the resistance to be as low as possible. So how do we do that? We use a core, which reduces the number of turns, and then we use a heavier gauge copper wire. And this gives me the proper Q value and gives me the bandwidth that I expect to see. So that's what the circuit looks like. Let's go over here now and we can take a look at the waveforms. Just bear with me while I set this up. Okay, so there's the voltage waveform, what we'd expect to see, 180-degree conduction angle. Okay, and we turn that off and we put on channel 2. There's the current waveform. Looks very similar to LT Spice and the values that we saw during simulation. And then we can look at both together. Here's the voltage, here's the current, and you can see we do have some crossover here. Okay, but certainly much better than the Class B amplifier. So here's where we have some power being dissipated, some power loss, some wasted power. But you can see on the other end, it's very, very little. So we're going to go ahead and measure the efficiency to see how that compares to the Class B and see the type of improvements that we realized. With that said, we should see a much lower operating temperature as well, right? We're dissipating less power in the drain of the transistor, and therefore we'd expect the case temperature to be significantly lower. So I'm going to go ahead and set this up so we can do the efficiency calculation, and I'll be All right, so before we look at the waveforms, I'm just going to briefly go through my setup again. I'm using a function generator. The output frequency is 13.56 megahertz. And as a reminder, this is a switching amplifier. So we're using a square wave with a 50% duty cycle to drive it. And here I've got the scope probe connected to the output side. So it's basically on the output side of the L network. So we're filtering out some of the harmonics and also doing the impedance transformation here. And then we'll be looking at the power supply. So we'll be monitoring the voltage and the current. We'll also be looking at the temperature here. And then we'll be looking at the output waveform on the oscilloscope. And what we'll do is we'll measure the RMS voltage. Just bear with me here while I set this up and get a good look at the scope. There you are. So we'll be looking at the RMS output voltage and then just applying simple Ohm's law. So it would be ERMS squared over 50. That would give us the output power in watts. And we can compare that to the watt meter. And all of this is into a 50 ohm dummy load, of course. So let's go ahead and power it up. And here we see the RMS voltage fluctuating a little bit, but let's call it 43 volts RMS. And here we have the DC voltage. We're at 24 volts at 1.75 amps. So let me just set up the camera to monitor the power supply. And let's do some quick arithmetic. I have a calculator here so we can calculate the values. So we had 43 volts squared, and then divide by 50, and I've got basically 37 watts of output power. So if we briefly take a look at the watt meter, you can see we're about 37 or so. Okay, and then we'll take the DC voltage times the DC power, 1.74, let's call it. Okay. So I've got 41.76 watts. Let's call that 41.8. Okay, and then we just divide one into the other. It'll give us the efficiency. So we've got 37 watts on the output divided by 41.8 watts from the DC power supply. That gives us an efficiency of 89%. So let's take a look at my original calculations here on the screen. And you can see when I first set up the circuit, I was looking at an efficiency of about 90%. So I'm within 1% of my original measurements. And now we can go ahead and compare the results of the Class B amplifier to the results of the Class C. And you can clearly see we were at 47.6, so make that 48, round it up. So 88%, 89%, so we're about 40% improvement in efficiency. And my original temperature for the Class B was 142 degrees. And let's go ahead and take a look at the temperature here, real time, 89 degrees. I measured 90 when I first set up the circuit. So we're looking at over a 50-degree Fahrenheit improvement, which is quite dramatic. And when I go ahead and put my finger on the device and touch the heatsink's actually cold. So I'm using a very large heatsink here, but just basically for convenience, that I could mount the board and also the DC to DC converter, which I use for biasing. But honestly, yeah, this heatsink is room temperature, and the device, as you can see there, the ambient is 79, the device case temperature is 89, so we're looking at about a 10-degree rise over the ambient, which is excellent. So there's the results comparing the Class B to the Class E, and we can see a significant improvement in the efficiency and significant improvement in the temperature. So here's the final circuit with the final values after optimizing them. And again, I used LT Spice plus the prototype circuit to find the optimal values, which are fairly close to the calculated values. And then for the sake of completeness, I mentioned Frederick Rabb in the beginning of my presentation. He also did some work on Class E and set up another full set of design equations. And those are actually captured in Keysight's ADS software. So this is the workspace that Keysight provides for Class E work. And what it does is it synthesizes the circuit for you and then tells you if you're within the safe operating limits. So this is a great tool as well. It's not a free download, it's quite expensive. So if we look at the results, there we have the circuit with the ideal switch in LT Spice, and you see we have the classical looking Class E waveform. Then we substitute with the IRF510. You see we have a similar waveform. I did some experiments with the biasing, trying to get this current spike down a little bit, which I was able to do. And then I did the same thing I did with the other tool, the online tool. I went ahead and removed the load network, and you can see significant difference in the waveforms and a lot more crossover and overlap between the voltage and the current. And then I captured the waveforms from the actual circuit. This provided me with similar results, but honestly, I think I prefer using the online tool from Tones, the tool that I showed in the beginning of this section. And yeah, and then using LT Spice, building a prototype circuit, and then measuring the results. So there's a summary. You can see the improvement. And again, I have a spreadsheet. If anybody's interested in it, I'd be happy to send it to you. And you can do your own calculations offline or go ahead and use the online tool. So that's it for the presentation. RF Man.